We have the ballistic pendulum. My title, ballistic pendulum, and hopefully you did the pre-lab. And these things were first invented in the 1700s, I think, or the 1800s. But when people made firearms, uh, now it becomes a little problematic about if you want to know the velocity of a bullet or a cannonball. Uh, you can't, like an arrow, maybe you can time it with this. Well, they didn't have stopwatches. And so it turns out a ballistic pendulum, yeah, it's a cool way to accurately measure a speed without having a an accurate timepiece. Isn't that something? I just realized that. But so our goal is to explain how it works. Explain how it works, and then demonstrate that it does work. We can't prove it because we don't have a real one. So we're going to use conservation of momentum. And let's see, the conservation of mechanical energy. We're actually going to use both mechanical energy. So, give me a minute. And so we're going to use both. And first of all, in collisions, and then in what's called with a conservative force. So we have to understand what that means too. So we have to define that. We learn that the mechanical energy is, but in momentum is always conserved. Hold on, I'm just looking at my notes here to make sure I don't screw up. Conservative, non-conservative. Right, so just that. Conservation mechanic. Yep. Ah. And then we're going to use the uh conservation, let's see, KE and PE. This is a part of conservation of mechanical energy with a conservative force, with only conservative force. And then we're going to apply this to a pendulum. And that involves using some trigonometry as well. So once we do all this, we'll have all the tools to explain how a ballistic pendulum works. just yell at me if you want me to go back. So this part, collisions, we've already seen, but we have this neat little sim here that I asked you to open. So we can revisit it. Oh, we're up to 13 of us. Okay. And so we can set it to being an elastic collision. And see what I've done. I've set the mass of the little one to be 0.5 kgs. I've set the mass of number 2 to 1.5 kilograms. And I've set the initial, you can't see what the initial velocity is unless you see these check boxes. So click these check boxes, and then you can see all these numbers up there. And you drag this vector to make it what you want. I wonder if I can type it in here. I can. Nice. 1, enter. Nice. That makes it easier. Okay. So what we can see here, we have a kinetic energy of, let's see how I can get these both on the screen. So we see that we have KE of, well, we can just do KE total. So we had KE is equal to 1/2 mv squared. So we have 1/2 0.5 kgs. And we have 1 meter per second squared. And that's pretty easy, 0.25 joules, because 1/2 of 0.5 is 0.25, and 1 squared is 1. And the other guy isn't moving at all, so that makes that pretty easy. And we see that the momentum is right here, mv. And again, we have our 0.5 kgs and 1 meter per second. And so it gives us 0.5 kg meters per second. Nice, right? So we can start this thing going. In fact, I can step it. And basically, it hits, it rebounds, and for sure, it has a different absolute magnitude of momentum. But if I add the two of them together, what's going on? Oh yeah, well we can't add them. We don't add the absolute values, of course. So we have a plus 0.75 and a minus 0.25, and of course that equals our 0.5. And we notice that, as we expected, the amount of joules, the kinetic energy total, hasn't changed. And we can calculate that. I don't want to take this to take forever, but you can convince yourself that it stays the same. Now, when we switch to completely inelastic, so that means that they stick together, as you recall. we notice that we have the two momentums, but now they're both positive. And if we add them together, one thing just to keep in mind here, that this sim only has two decimal places, right? So 0.13 and 0.38 are actually 0.125 and 0.375. And you can do the math yourself. So we notice that the momentum stays constant, but notice that and this is, I calculated it. Where is it? I thought I calculated it. Oh yeah, it's 0.0625. It just rounds it. What I find interesting here is that I've got now let's see, it went from the kinetic energy was all in the beginning, the kinetic energy was all in the 0.5 kg mass. And then now when I have a 4 kg mass total, oh, no, it's not. It's 3 kgs. Never mind. I'm not going there. I'm not going to say something stupid. I noticed that it went down by a fourth, but the mass didn't. Oh, the mass did go up by a fourth, 4 times, because the initial, no, I got it right. I didn't write it down. See, if you don't write things down, the original mass that had KE was this much. At the end, it was this many kgs. And so this is kinetic energy initial. I noticed that this is KE initial over 4, and it's 4 times bigger. So the bottom line is that when we have the elastic collision, we have to take the total mass and whatever is the resulting V. Now, the thing that goes on here, though, is that how do you know what the resulting V is ahead of time? And the way you get the resulting V, though, is because you can use conservation of momentum. So let's do that. Back to being a mouse. So we had one mass going into the larger mass, and it was 0.5 kgs, 1 meter per second. So now the momentum is 0.5 kg meters per second. And this one had 0. And so at the end, give me a minute. If they're elastic, then we have capital M plus little m times V final has to equal. So we can get our V final. And then our kinetic energy is simply M plus M times V final squared equals our KE final. So we know everything we need to know about inelastic collision, inelastic. And this is what they say, completely inelastic. They stick. See, now I have a plan to get that. Oops, question, or just somebody unmuted by accident.
Professor, yeah. Can you? I ran to the restroom for the 5th slide. Can I just? Yeah.
Yeah. You can also Guillermo, you can see it in the sim as well. If you plug, you guys can use the sim at your own pace and make sure you see how this all works.
Okay, thank you.
You're welcome. But I don't have any issue with moving it back. And of course, hopefully this is all familiar. Oh gosh, I forgot to restart the local recorder. I noticed that even when I record locally with Zoom, it goes to the Zoom site first and comes back. So all the artifacts from the internet are still there. And I wanted to record this locally, but I forgot to start the recorder. But it's being recorded on Zoom. Okay. So we need to use the conservation of momentum, and we also exploit the fact that they stick together. That's what sticking does for us. And it's a simple matter to calculate what the final velocity is. When you have two of them elastically, yeah, I don't think you have enough information. That's funny. I should remember this, right? They hit together. And well, if you know ahead of time that the kinetic energy has to stay constant, right? Total kinetic energy. I suppose you can figure out how to get the V finals. That's funny. I should know that off the top. You see, remember I said that my hero, Richard Feynman, said that physics is this big bridge that has way too many pieces and pieces fall off and we have to sometimes pick them up and stick them back on. I can't remember off the top of my head if I only know one of the initial velocities in an elastic collision, can I figure out the two final velocities? I think the answer is no, but I can't remember off the top of my head. But that's fine. You know, I know that many a professor or in high school, you're not supposed to do that. You're supposed to appear perfect all the time. I think that's bad when a professor tries to appear perfect all of the time. Of course, I'm not, right? But I'm still not a dummy, right? And I still am a fairly successful physicist. Okay, so let's take a look here. So we see how, so we are going to exploit from our collision knowledge for the ballistic pendulum, we're going to exploit the inelastic collision. And we should know from the pre-lab, or we should say, oh, wow, that's right, that a ballistic pendulum is an example of an inelastic collision. And it's set up that way that the bullet stays in the target mass. So what's next? We have to know, okay, what is conservation of mechanical energy with a conservative force? So in the collision lab, we had a spring, but once the spring, we didn't really talk about the forces involved. We just used the spring to set the car at a certain speed, and then we forgot about the spring. And I may have mentioned conservative forces and non-conservative forces and friction, which is a non-conservative force, but we didn't really get into it. But today we are. Excuse me. Hey, babes, come and say hello. There's the camera. My daughter just has arrived. On the dishwasher in there, if you like, I bought you 2 new Fabi things, and there's a list of instructions. You're gonna love it. It's like rubbing your tummy, pat your head, walk out the door, and shout to reprogram it.
What? Okay.
Go look at the instructions. You'll see. They're all in the dishwasher. She wants to get going in a few days, so we're gonna install a new stereo, and I bought her 2 new key fobs because the one that came with the car is crappy. But you can't believe the instructions to install it. And open the door once, twice, shift it into park and reverse, and it's really stupid. Okay. So now, okay, so let's go to, excuse me. So we want the skateboarder. That's one of the other sims I asked you to set up. And turn on the grid. Also notice you put it in this intro. There's different choices on the bottom. In fact, you can make your own roller coaster if you want. So we want intro, turn on the grid, turn on the speed, stick to the track. And so this is one that's interesting. I wanted to, well, I did a calculation a minute ago. I'm pretty sure the gravity is the gravity of the Earth. So don't touch the gravity slider. I set her weight to 50 kilograms just to make calculations easier.
Wait, is this sim on the one of the modules?
Yeah. Go to here and conservation of energy sim.
Okay. All right, thank you.
Welcome. Yeah, I just added them this morning. So so it didn't. So I'll just get mine restarted. We want the grid. Want to click here where it says energy. And we want to see her speed. Don't touch the gravity slider or the friction slider. And we can set her 50 kilograms, just makes it easier to do calculations. And click the pause button. Put her at slow. And now notice that when I lift her up, notice the energy increases, the so-called potential energy. Now, when I put her on the track, also notice, and in fact, we can do this at normal speed for the time being. Notice that she always comes back to the place that I started her at. And the thing that's making this happen, of course, is gravity, right? When we roll the marble, we know something about this because we roll the marble down a track. Now, one of the really interesting things about this that, and I guess this is like Hannah interrupted me, but remember, like if I have a ball in my hand, and I throw the ball up in the air, of course, it comes back down. Now, the thing to notice is that at the top, the speed is equal to 0. Notice that when she gets close to the top, to the point she started at, the speed comes down to 0. Well, it didn't give me the very last point. But her speed started at 0. And when she comes back up, it stays at 0. And in the case of me throwing up the ball, when I throw the ball up into the air, whatever speed that it left, it comes back down with the same speed. So if I take her, let's see what we can't do that here, but all right, let's set her there. And let's bring her down to the bottom. So let's make believe I don't have, and I looked, yeah, I can't set her at an arbitrary speed, unfortunately. So when she's on per second, so if I give her those initial conditions, and I turn her loose, she goes up to the top, back to the very same height. Her speed goes down to 0. Well, this sim doesn't have enough steps. Notice it was 0.1, it was going down, and now it's 0.1 again. She stops, she starts to come back down. And at the bottom, well, I can't, she's a little bit past it. So I think that her speed is actually 10 meters per second. So she comes back with the same speed that she started with. So that's because we call gravity is a conservative force. Notice conservation. Basically, what it says is what you put in you get back. And the best way to look at this is in the so-called energy formulation. Instead of using 1/2 AT squared and such, we use energy formulation. And we already know about kinetic energy. So now we have another thing called potential energy. Potential energy. And if you think about it for a minute, scratch your head. Oh, right. If I put something in, that means that I'm increasing its potential, right? I want it to do something for me. So I can sort of think of an idea. Okay, I know potential energy is I'm going to put something into a system. I'm going to add energy to it, and I can get something back. So for a conservative force, and most especially gravity, for any conservative force, this means that there exists a PE formula. So for gravity, it equals to the mass times the acceleration of gravity times the height. So if we take our young lady here and we set her at 5 meters high, unfortunately, this graph doesn't give numbers. Let's calculate the PE of our skateboarder. She is 50 kilograms. She is the acceleration of gravity, sometimes also called G, equals 9.80 meters per second squared. We know something about that from the Marble Lab. And we've set her height to be 5 meters. And so take our calculators. Let's see, did I get it right? Yeah, I already calculated it. But you guys should double check me. I guess I should ask you guys to tell me what it is. So make sure everybody calculate this. Write this down and make sure maybe I made a mistake. And the units are joules. kg meters squared per second squared. Kg meters squared per second squared is a joule. Yeah,
I had got I got 245, not 294.
295. Maybe
245.
45. Interesting.
Okay. I'm looking at the wrong thing.
No, it could be. Oh, sorry. I put 6 meters in my notebook. There you go. Let me retype. 50, enter. 9.8 times, and then 5 meters. Yep. So there we go. Calixto earned his pay today. Okay, so let's see now. Let's test out this idea about we can get something back. Now, first thing we already know is that she's going to be able to get back to the same place. But let's see something. Let's get her back to the bottom. Just past the 9.9 meters per second. Okay, well, why don't let's calculate the kinetic energy. So that's 1/2 mv squared. And 9.9 meters per second. And this time I'm going to wait for you guys to tell myself and Calixto what is her kinetic energy. So please either say it or type it into the chat. So Janelle says 247. Okay. 247. 240 with a question mark. 247 from Janelle. 0.5, and I get from George the same, but Karen gets 245. Okay. So I get let me try it. 0.5, enter, 50 times, and then 9.9 squared times. Now I got 245 myself. I wonder where 247 comes from. Interesting. Try typing it again, guys. Maybe you didn't
for the
clear
people who
something.
got 247, they didn't square.
Ooh, but then you would get a much smaller number. Then maybe they also forgot to use the 1/2, right? Good question. Let's try that. 50, enter, 9.9 times is, nope. Oh yeah, then times 0.5. 248, or yeah, but boy, that's weirding me out. Because I'm basically then, what's wrong here? Oh yeah, because if I multiply it by 9.9, it shouldn't be, wow, now I'm weirded it out. How did that work? 0.5, enter. 50 times 9.9 times, and I get 248. If I go 9.9 times again, I get, 2450. Is that right? So it seems like we did something wrong over here then. 50, enter, 9.8 times, 5 times. Yep, see? All right. Now it makes much more sense. See that's why, guys, I'm not perfect. I need you guys to stay awake and stay on top, okay? So notice that the kinetic energy at the bottom equals the potential energy at the top. And also notice at the bottom.
Wait,
Oops.
is it supposed to be 9.9 or 9.8? Because they're discussing in the chat.
Oh yeah. I'm sorry, I missed it, Janelle. Okay. Watch this. 9.8 is meters per second squared, right? That's the acceleration of gravity. 9.9, notice the squared is on the outside of the parentheses because it's this here. And it's an unfortunate coincidence that her speed is 9.9 meters per second. Does that make sense? Not yet. Oh, because they did. Yeah, that's exactly right, 9.9 meters per second. Yeah. Yep. Yeah, and of course I screwed up a little bit too, Janelle, don't forget. Yep, right, yeah, that's all right. It's all good. All right, but it shows you a common mistake. And in my case, I didn't look carefully at I have my calculator set up in scientific notation. I should change it to just regular numbers. But anyways. And it's funny, I did, you should see, I'm really prepared for class today. I took all kinds of notes and what I wanted to do, although I'm not completely following it. The first casualty of battle is the plan. Excuse me. Now, so let's go back to the sim and let's just turn it loose. Notice, the total energy stays constant. Total mechanical energy, anyway, because of course the conservative force in question. So when you have a conservative force, the total mechanical energy is constant. So the E total then also equals the KE plus the PE. So one thing to notice, and let's see if I can get this going on. Let's put her, it's pretty close to 2 meters, right? So it says here, when h is equal to 2 meters, speed is equal to 7.7 meters per second. So we have 1/2 50 kgs times 7.7 meters per second squared plus 50 kgs, 9.8 meters per second squared times 2 meters. Let's all calculate that now. Hope this is going to work out. Top everything else, my calculator buttons are sticky. I can do this one in my head. Carry the 1. And what did we get before? 2450, 2460. Well, because probably we don't know that number very well. I don't think that it's on here. Let's take a look. The grid. Yeah, reference height. The trouble with that is that it just sets whatever the 0 is, and that's not very helpful. So we can't figure out exactly how high she is. Yeah, she looks like she's a little lower than 2 meters. What happens if we, and now she's too high. There is no, I wish there was a stepping back button. So, also then, I guess I can keep this here, maybe. Let's see how clever I am. Let's just see, huh? So for a conservative force, the mechanical energy is constant. So this also, what this implies, and it's used the usual strategy too, if you do these for test or homework problems. Usually what you do is you find PE max, and then this means KE is equal to 0. Or KE max. And this implies then, well, this means that PE is going to be equal to 0. Once you know either or, then you know everything. Because you know that this sum has to be constant. So usually what you do then is you look at how high something is. That's what's the beauty of energy. You notice that she has a velocity vector that isn't pointed straight down. But whether she is, let's see if I can easily show this. I don't know if I can or not. Let's get the grid back. Right. If I can make this both here. They're both at 6 meters. So if I put her here, see that? She goes right back up. Her total speed will always, for any given height, and let's put that up here. And we can step that. So let's see. So get her to 5 meters. Whoops. Now I can't touch her because then I'll change the total energy. 4.4 meters per second. Look at that, 4.4 meters per second. Her total speed is always dictated by how high she is. It's a little bit different when you do like we did the marble lab. We didn't use the energy formulation. And I don't know if you guys are doing projectiles or did you guys do in 1560, did you look at projectiles? X and Y motion? Anybody?
In my class, we haven't yet.
No, I wonder if you will. Okay, so I don't want to confuse you guys. The energy formulation is way easy. I always tell students when I teach them all about vectors and like the marble lab, and I say, all right, now we're going to do energy and you're going to hate me. And because when you have a conservative force, and let's just add a little bit to be really, because we need this concept in a little while. If we prepare a system so we put the girl at a certain height, because when we want to have no external forces other than no external force except gravity. So notice that when I'm moving her around, the total energy changes. And unfortunately, it doesn't seem like, yeah, I can't give her an initial speed, which is too bad. I would have liked to have been able to do that. Can I do that with her? No. Well. So you prepare the system. That's an important concept because we're going to look at, when we look at the ballistic pendulum, the energy stays constant because now my pushing her up the hill is not a factor anymore. It's only gravity working on her. Now, it's not important for us for this lab, but a non-conservative force is friction. So if I add friction, oops. Is it, no, we got to restart her. Oh, what happened? It won't. Well, I broke it somehow. Oh, there's lag. Okay. Oh, and I know what this thing is. What does that do? Oh, well, I'm just going to have to reload this. I hit too many buttons too quickly, and I sort of lobotomized it. Wow. Lag is us, huh? I'll just see. So I wonder, is this the network or is this my computer? Whoops. Well, I can sometimes give the computer a little kick in the butt. Yeah, sort of slap it in the face. Let's see. Yep. There we go. Now, the only problem with this thing here is that when oops, forgot to pause it. So I prepare the system. And we see a certain total energy. Now, if I add a little friction, unfortunately, what happens is the way they do this, the total energy is staying constant, which that's why I was careful to say total mechanical energy. This is not the total mechanical energy. This is energy total because you can't create or destroy. It just changes form. But when you have a non-conservative force, you notice that eventually, which unless she pushes with her foot, she eventually comes to a rest because the friction is converting the mechanical energy into heat. Excuse me. Okay. Well, it's going to take a while for it to stop at the end. Usually people get bored and they jumped off the skateboard already, right? All right. So with a conservative force, when gravity is an example, the total mechanical energy is constant. And once we know what E total is, we can always predict what the KE and the PE is, and usually by looking at the PE. And to find E total, you generally want to see what is the PE max or what is the KE max. And in the case of the ballistic pendulum, we are going to get the KE max, FYI. The ballistic pendulum, we look for KE max. Okay. Let's take a look here. So conservation of momentum, mechanical energy, and then there's in collisions, then with a conservative force, and KE and PE. So we've gotten up to there. We haven't looked at a pendulum yet. So we have almost everything we need.